Okay, so I think the live stream is now online and we're recording. So I think we're good to go.
All right, I am ready when you are, Steve.
Cool. Well, do you want to go first, Steve, or shall I? Since we're going to seamlessly move into actually starting the conference now.
That's right. Yes. Welcome to Sazerac, everybody. We're very glad to have you here. And so Steve and I just have a few notes of welcome and logistics before we get started with a wonderful slate of science talks. So first, we're going to introduce ourselves. I'm Steve Finkelstein. I'm one of the co-chairs of the Sazerac SOC. I'm from the University of Texas at Austin.
And I'm Steve Wilkins, again, one of the other co-chairs of the SOC of Sazerac, and I'm from the University of Sussex.
We have a wonderful group of SOC members, and they'll be helping us run the conference during the week, but they've also done a lot of work helping us plan the conference. So I just wanted to recognize them very briefly. It's Caitlin Casey from UT Austin, Anson D'Aloisio from California Riverside, Marusha Bradich from California Davis, Romil Dave from University of Edinburgh, Xiaohui Fan from University of Arizona, Charlotte Mason from the Harvard CFA, Pascal Ush from the University of Geneva, Masame Uchi from the University of Tokyo, Laura Pentorici from the Observatory of Rome, Renske Smith from Liverpool University, Aprajita Verma from Oxford. And so just a reminder why we're actually doing this, and it seems a while since we actually planned the conference, but it was beginning to be quite alarming after the pandemic hit when all the in-person conferences were being canceled. And obviously that was very necessary, but for our field, and particularly for junior members in our field, that had a very negative consequence. And so Steve and I started talking and brainstorming, how can we give people the opportunity to talk and share their research? And that led to this Sazerac, or Summer All Zoom Epoch of Reionization Astronomy conference. And so the goals of Sazerac were to prioritize talks by junior researchers. And we had so many submissions that the only talks we were able to give were by students in their last 2 years of their PhD or first-term postdocs. There are wonderful, wonderful talks by both more junior and both more senior members, and some of them have submitted via YouTube, and we'll have them on our website, and others may submit posters to the Slack channel. We also wanted to take advantage of the additional time that we now have to prepare Cycle 1 JWST proposals by learning about the latest results. And finally, just to bring our community together to share exciting science and have a little semblance of normalcy, if only for a few hours during a day, during these unprecedented times.
Thanks for that, Steve. So the next thing that we wanted to mention is a very sad thing, and that was the recent passing of our friend and colleague, Olivier Lefebvre. I'm sure many people who are in this meeting today have interacted with Olivier over the years. Certainly me and Steve have, and I'm sure many other people. So for that reason, we really just wanted to dedicate the entire conference to Olivier's memory, and we send our condolences to his friends and family.
Yes, thank you, Steve. And one other thing we want to acknowledge is the movement that's been going across the US, which led to the original delay of Sazerac. So the Sazerac SOC just has a small statement we'd like to read, and we're actually going to read it again at the beginning of the second session today for those who aren't here. So we've been saddened and deeply troubled to have witnessed the tragic murders of George Floyd and Breonna Taylor at the hands of the police, and the subsequent use of excessive force against peaceful protesters across the US. Systemic racism permeates all aspects of our society, including academia. These current events show why it's incumbent amongst all of us, especially those more privileged, to fight harder for true equality and justice. We originally postponed Sazerac to give our community the time to reflect on how we could work to improve our society, and this delay has provided, hopefully, people space to focus on this crucial issue now. At many of our institutions, these events have led us to examine the deeply embedded systemic barriers to Black, Indigenous, and people of color at all ranks in our departments. It is our hope that this newfound energy to drive structural change does not wane, and we truly move towards a more diverse and inclusive community. During today's break in between the two sessions, we will have a short discussion allowing members of attendees of Sazerac to share ideas of how they are trying to employ such change at their institutions, and we hope to have a follow-up discussion on Wednesday. We also encourage Sazerac participants to engage in the discussions in the Equity and Inclusion Slack channel. Finally, since Sazerac did not have a registration fee, if you're willing and able, we encourage you to donate to anti-racism causes, particularly those which support the Black Lives Matter movement, or to volunteer for related activities.
Thanks for that, Steve. So it's now my job to mention some of the logistics of today. So obviously, I think this is the first time that many of us have maybe engaged with a virtual conference in this way, and certainly it's the first time that I've had running one. So I think probably the most important thing is questions. We do want questions from the audience. The way that we're doing this was outlined in the email earlier or last week, but the way we're going to do this is via the Slack channels. So if you go to the Slack workspace, there'll be a channel for each session. And within each of those channels, there'll be a thread for each talk. And the chairs will be monitoring those threads for questions. And so do put your questions there. And the chairs will then actually read out those questions at the end of each person's talk. We felt this was the most seamless and efficient way of doing it. And it also allows us to keep these questions for later. And so as well as answering them live, we hope that the speakers will also be able to answer them maybe on Slack as well. So people who weren't watching live can also see the answer there as well. Just a few other things. So you also see that there are other features on Slack. So we have a technical support channel. So if you are having any problems, either as a speaker or as a participant, then do send us your concerns there. Obviously, if you can't access Slack, you can feel free just to email us and we can try and figure out. There's also an equity and inclusion channel. There is a feedback channel where you can give us feedback on how Sazerac has been run. There are also some themed channels on Slack where people who don't want to submit a recorded talk can also add a poster, a slide, or a figure and respond to any questions. So if you do just post a figure, then do provide a short description of what you're posting there. And if people do ask you a question there, then do please answer it as well.
Just a few other reminders. So we, in addition to the discussion break today, we do have one plan for every day, or sometimes more than one. We put that in an email last night, and we will, I'll post that in the general Slack channel here in just a little bit. And finally, we are about ready to get on with our talks. And so a reminder to everybody, but especially the speakers, the talk slots are 15 minutes. And I know we're starting late because Steve and I have talked a little bit. So 15 minutes when we start. And the idea is you have about 10 minutes to talk, a couple of minutes for questions, and then a couple of minutes to start the next speaker. Our goal will be to stick to time as much as possible in case people are coming and going to hit particular talks. So with that, I think we are ready to go, unless I missed anything, Steve.
No, I think that's everything. This first talk is going to be slightly different because I'm actually going to show Chris's slides today because of a technical issue, but he should be doing the speaking. So I'm going to stop my video now and start sharing, hopefully, Chris's slides.
All right, so our first talk is by Chris Lovell called Introducing Flares, the First Light and Reionization Epoch Simulation. So Chris, when you're ready, you can unmute and go ahead.
Okay, can everybody hear me?
Yes.
Great. Okay, thank you very much to the Steves and to all of the organizing committee for organizing this fantastic conference. It's a real privilege to be the first speaker and introduce flares, the first light and reionization epoch simulations. So this is work that's been done with a number of people on the left there at Sussex and further abroad, and also the larger Eagle collaboration. I'm just going to present the first results from this detailed in the archive link at the bottom left there. Next slide, please. So what is FLARES? FLARES is a series of 40 Zoom simulations using the Eagle full hydrodynamics model. These are selected with a range of different overdensities. As you can see from here, this is the dark matter distribution in all 40 regions. So we pick underdense regions and a number of very, very overdense regions as well. And each Zoom simulation has a radius of 22 megaparsecs. Next slide, please. So we select these regions from a large 3.2 gigaparsec cubed dark matter only box. So this has a resolution of 10 to the 10 solar masses per dark matter element. So it's quite coarse, but it's sufficient to resolve the large scale structure. These are selected at redshift 5, And you can see compared to the periodic eagle volume, which is inset in red, and the periodic blue tides volume, we're able to sample a much larger range of different environments than in typical periodic hydrodynamic simulations. So the purpose of doing this is not only to study how galaxy evolution during the epoch of reionization differs in these very different environments, but also to combine these regions together to build composite distribution functions that can significantly extend the dynamic range compared to smaller periodic simulations. Next slide, please. So just looking at the raw number of galaxies that we get in our regions, on the left, you see a cumulative distribution plot against stellar mass. The dotted lines here shows the periodic eagle volume, 100 megaparsecs on a side. And the most massive galaxy in this region at redshift 5 is around 10 to the 10.5 solar masses, whereas in flares, we are able to simulate tens of galaxies above 10 to the 11 solar masses. And at around 10 to the 10 solar masses, we actually generate 20 times more galaxies at that mass. So we're producing a huge number of galaxies that are interesting to study. But if you look at the figure of merit on the right, so this shows the dark matter resolution on the x-axis against the simulated volume for a number of different simulations, hydrodynamic or not. And there's a general trend between the size of the resolution, size of the volume you can simulate and the coarseness of the resolution you have to deal with. So flares is done at the same simulation as the periodic eagle volumes, similar to illustrious and to blue tides. However, by combining these together with the to mimic the effective volume of the 3.2 gigaparsec box, we're able to significantly extend along the y-axis. Next slide, please. So which regions did we select and how do we combine those? So we selected a range of different overdensities shown on the left. We measure the overdensity on a very fine grid throughout the 3.2 gigaparsec volume, and then selected those with quite low underdensities in void regions, a number of mean density regions, but with a particular focus on these very overdense extreme environments as well. So the plot on the right, the solid line shows the distribution of overdensities in our flares regions, and then the blue histogram shows the overall log normal distribution of overdensities throughout the box. And we essentially weight these by combining them and weighting their fractional contribution to that overall distribution. If you're interested in the details, please refer to the paper. Next slide, please. So what does this look like in practice? So this is the galaxy stellar mass function on the left in flares from redshift 5 to redshift 10. And you can see there's a very strong double Schechter-like shape to the mass function, even up to these very high redshifts. And the characteristic mass, or the knee of this, it actually evolves with redshift from around 10 to the 9 solar masses to 10 to the 10 solar masses. And compared to the periodic eagle volume, which is shown on the right, so the dotted lines here are the measured double Schechter in flares, and then the points here are the measured stellar mass function in the periodic volume. The exponential tail is completely unprobed in this periodic volume. So it shows the value of incorporating these overdense regions to actually probe this tail. However, at the low mass end, the slope is actually in good agreement with the periodic simulations, which gives us some confidence in our weighting procedure. Next slide, please. So compared to the observations, flares kind of sits between the interstudy scatter, even up to the highest redshifts. Unfortunately, unable to completely probe whether this strong double Schechter extends to higher redshifts. However, compared to other models, such as blue tides and some of the semi-analytic models and the fire simulations, we don't see this strong double Schechter shape in those models. So we see a more power law-like or single Schechter-like shape. So one explanation for this may be that these very overdense regions that we're able to capture with flares contribute significantly to the high mass end of the galaxy stellar mass function. And these sorts of regions are simply not captured in these lower volume simulations. Next slide, please. So we can also look at the star formation rate function. So it's shown on the left. It also shows a very strong double Schechter-like shape. However, the characteristic star formation rate does not evolve with redshift in the same way as the characteristic mass in the galaxy stellar mass function. And this is telling us something about how feedback works in the Eagle model at high redshift, and it's something we're investigating now with relation to the halo mass function. So compared to the observations, we see slightly more tension at the, oh, gone too far. Compared to the observations, we see slightly more tension at the high star formation rate end, slightly higher normalization. But at higher redshifts, the observational constraints aren't enough to rule that out, sort of thing. And compared to the modeling constraints, we again do not see this strong double Schechter shape. But again, this may be due to the lack of these very overdense regions probed. Next slide, please. Oops, I think we've missed a slide. Thanks. So not only can we combine these regions together, but we can also look at the overdensity distribution. We can also look at the dependence of these distribution functions on overdensity. So the left two panels show the galaxy stellar mass function, and the right two panels the star formation rate function. And there's a general trend with normalization and overdensity as expected. But we also see a strong dependence on the form of each of these distribution functions, where the most overdense regions tend to show this stronger double Schechter shape. And it's these regions that tend to dominate the number densities at the very high mass or very high star formation rate end. Next slide, please. So finally, we also looked at the star forming sequence. So on the left, you can see there's a general decrease in the normalization with decreasing redshift as expected. We also measure a very strong double power law-like shape with a turnover that evolves similarly to the knee in the galaxy stellar mass function. However, we don't see any dependence on overdensity. So even the most overdense regions, whilst extending to higher stellar masses, do not show any difference in the star formation rate at fixed stellar mass. And this is in agreement with a number of observational protocluster studies at slightly lower redshifts of 2 or 3. Next slide, please. I think we skipped one. So that was the flares first light reionization epoch simulations. I think we've gone back again. But essentially, yeah, just like to wrap up there. And you having trouble, Steve? There we go. Don't click anything. Okay, so I'm just going to wrap up there. If you are interested in reading up on some more details, then you can find them at the archive link on the bottom left. We also have a website, flaresimulations.github.io, where you can find more information, visualizations, and data products. In the future, we're looking at some of the passive population at the high redshifts, galaxy sizes, a number of predictions for the upcoming Euclid and WFIRST observatories, and some of the black hole properties and other things. But if you're interested in any of the data products from flares, then please do get in touch. We're happy to make things available, and we'll be releasing data products in the near future too. And Aswin should be up next, showing results for the UV luminosity function. Thank you very much.
All right, thank you, Chris. So I had one question before I lost my ability to see Slack, which I'm working on, but the question was from Aaron Young, and he was asking if you could talk about why you see this double Schechter function at higher redshifts, so where you think you see this.
Yeah, so the Eagle model, essentially has two forms of feedback, AGN and star formation feedback. It's obviously not expected that AGN feedback plays a very strong role, particularly at redshift 10. However, there is a temperature dependence to that AGN feedback in the model. And at these high redshifts, where the overall gas temperature is a lot lower, the actual AGN feedback may be a lot stronger at lower masses. So this is something we are actively looking at, but it's still kind of up for debate at the moment, but very, very interesting. It may be something particular to that AGN feedback in Eagle at these very high redshifts.
Okay, thank you. And then a follow-up from Tom Thunes. He said, presuming the exponential cutoff is due to AGN feedback, have you looked at the AGN luminosity function?
So that is something we're looking at now. So Steve has a student who's studying the AGN luminosity function, very much in early days with that at the moment, but it's certainly something we're very, very interested in to try and link to this double Schechter shape that we see in the galaxy stellar mass function and the star formation rate function for sure.
And there's a question from Anna Schauer who asks, what star formation models do you use? Do you include population 3 stars?
So we do not include population 3 stars. At the moment, this is essentially using a slightly different calibration of the Eagle model called AGN-DT9, but it's essentially very close to identical to the fiducial Eagle model. So it was tuned to the Z=0 galaxy stellar mass function and also to galaxy sizes at redshift 0. But aside from that tuning, the model that we use was not tuned at high redshift, so all of this is predictions at high redshift. However, it doesn't include any particular population 3 like extra modeling or anything like that. This is the vanilla Eagle model. So it's interesting to see how well this does at these Epoch and Reionization kind of eras. I don't think the resolution is particularly good enough, for example, to resolve the kind of population 3 star formation at slightly higher redshifts. But that's something we'd definitely be interested in future iterations of the model, where we're going to look at increasing the resolution and studying some of the first stars.
Okay, and a couple more questions about the missing double checker on the observational side. So you, from Enrico Garaldi, said, you mentioned it may be due to the larger volume probed. If you restrict flares to a smaller volume, do you still see this double checker?
That's a good question. So it's a kind of a trade-off, right? So if you restrict the volume, unfortunately, you then you're not able to include those very, very overdense regions simply because you're using a smaller periodic volume. So there are, so in the periodic 100 megaparsec volume, you only get 2 or 3, greater than 10 to the 14 solar mass clusters at redshift 0. So those protocluster environments at high redshift aren't very extreme. So there's this kind of trade-off between, you go to this very, very large box and you're able to capture these protocluster regions, but you can't.
Okay.
Yeah, I think I can see what you
I'll
mean.
give you one last.
Oh, go on.
Oh, sorry, I was going to give you a follow-up, but go ahead and finish.
No, go for it.
Okay, so one last one about the double checker, and then we'll move on. This is from Christian Finlater. Christian says, the double checker form looks as though it might reflect reaccretion of expelled gas into massive halos. Can you run a no wind model to rule this out?
That's interesting. Yeah, so we're looking at some of the modifications to the AGM feedback, but some of the star formation feedback was not on high on our priority list. But if that's something that there is maybe evidence for in some of the higher resolution Zoom simulations from other groups, then that would be super, super interesting.
Okay, great. Well, thank you, Chris, very much. And we'll move on to the next talk. The next speaker is Aswin Vijayan, who will show us photometric properties of galaxies in the flare simulation. So Aswin, if you can please share your screen and unmute yourself and begin when you're ready. And a reminder, I see our attendee list growing. If you would like to ask the speaker questions, please go to our Slack workspace for this conference and find the session. This is session 1A, and then you can find a thread for the speaker and you can ask them there. And apologies, I didn't get to all the questions for the first talk, but we've asked the speakers to go through later on today and respond to all the questions there. All right, so take it away, Aswin.
Oh, hi, can you see my screen and hear me?
Yes.
Oh, thank you. Hi, I'm Aswin, PhD student at the University of Sussex, working on the flare simulation that Chris just introduced. I would like to thank the organizers for giving me this opportunity to talk about my work. And I'll go on and talk about the photometric properties of galaxies in the flare simulation. As Chris has already given us a comprehensive introduction to the flare simulation, I'll skip some of the pleasantries of the flare work and move on directly to reiterate another point, which is about the effective volume we are probing with this big box that is available to us. So this effective volume gives us access to the large-scale power available in the 3.2 co-moving gigaparsec volume at the Eagle reference resolution. With the use of our weighting scheme, this allows us to extend the dynamic range at the bright end So this is really complementing the upcoming new generation telescopes like Euclid, the James Webb, and the Roman Space Telescope. So with this effective volume and the large number of galaxies that were shown by Chris, we'll now show some of the photometric properties of the galaxies that are generated in the simulation. So I'll briefly introduce here how the photometry of the galaxies are being generated. So for modeling the photometric properties, we adopt a simple line of sight dust extinction model. So I show here a cartoon representation of the method. Uh, we use BPAS to generate spectra for each star particle in the simulation, treating them as a simple stellar population. We trace this along the line of sight, which is the z-axis in our case. The starlight is attenuated by their birth cloud component as well as the intervening interstellar medium. Now we assume that this dust content is proportional to the metallicity of these components. There have been a few studies which have shown that there is a gradual evolution in the metallicity, but we ignore this for this work and will try to probe that in a future work. Now these two are the free parameters that are introduced in our model, which is the attenuation introduced by the ISM and the birth cloud. Now we calibrate these two values so that we retrieve the Z equal to 5 UV luminosity function from Pavens et al. 2015. The birth cloud component is fixed by a simple visual inspection of some of the properties like the UV continuum observation at Z5 and the line equivalent with measurement Z equal to 8 from DeBarros et al., which shows the O3 doublet. Now, these are generated using this publicly available SynthOps module. The link for that is given below. You can go around and play with it and see what all properties of Galaxy you can retrieve. Now with this modeling, I'll show some of the photometric results that are generated from the FLAIR's galaxies. So first we have the UV luminosity function. Here I show the UV luminosity function of the FLAIR's galaxies from Z equal to 5 to Z equal to 10, which are the colored circular data points in the figure. Plotted alongside is some of the observational results as well as some of the modeling studies. As you can see, we do provide an excellent match to the observations at all redshifts above Z greater than or equal to 5. One thing to note is that we do predict slightly lower number densities of bright galaxies that are predicted from the Schechter fits of some of the some modeling studies like Mason et al. 2015 and Ma et al. 2019, the fire simulations. And these can be seen at redshifts above Z8 and Z9. So there could be an argument for the fact that we might still not be probing some of these brightest galaxies in the universe. But these are Schechter fits from their modeling, and it should be taken with a grain of salt. So we also try to provide functional fits to these data points, and we try a Schechter form as well as a double power law form, and we see that the Schechter form is a better fit to redshift 6, 7, and 8, while the double power law is a better fit to the other values. This was inferred using the Bayesian information criterion. So there is another instance where we see that there might be some brighter galaxies that we still need to probe to actually look at what functional form these galaxies do actually follow. This is something that we are interested in doing later. Now we look at the UV continuum slopes of the galaxies that are in flares. We can see that it provides quite a good match to the observed values, but the observations are you could say that it's kind of all over the place. So it's hard to constrain if these are actually providing the right values or not, but we do provide a good fit to these observations. We also see that the flares galaxies have a flattening of the UV continuum values at the brighter end. This is something that I've been seen in other works of a flattening, not a clear flattening, but like the UV continuum slopes are much flatter than some of these observations show. But this is what the flares galaxies are showing. We also look at the attenuation in the far UV of the flares galaxies. What we can see is the attenuation is increasing with increasing intrinsic luminosity, which is expected. One thing you can see is some of the brighter galaxies that are in some of the intrinsically bright galaxies in flares are in the most attenuated. We also see that some of the galaxies have already moved on to the passive regime by z equal to 5. This might be much clearer if you plot it as a function of stellar mass, where you see more of these galaxies popping up. This is something we are studying at the moment. And we also show the environmental dependence of the luminosity function. So here I plotted the UV luminosity function as a function of the overdensity of different regions. And as you can see, the normalization is higher for higher overdensity, which is expected. We also see that the highest overdensities tends to follow a Schechter form with a hint of a double parallel features at some of the intermediate overdensities. And in black, you have the composite function, which is being probed by some of the mean density regions. So it is a really good match to mean density volumes, our composite function. We also see no environmental dependence on the attenuation in the far UV. So here is the attenuation as a function of different overdensities, and we see the same behavior for the dust attenuated far UV luminosity. Now I compare some of the observations of the equivalent width measurements that we have from the flares galaxies compared to the observations. So here I show some of the observational measurements from Ryan Ensley and DeBarros 2019. We do predict, we do provide a good match to these observations, but as you can see, we fail to account for some of these high equivalent width galaxies. This could be because we don't model the effect of AGN luminosity into the effect of AGN into the luminosities that we are generating. So this is something that something that could explain some of these lack of high equivalent width galaxies. So this is something that we are looking into with one of Steve's students. And we also look at the C3 doublet here. Since we don't have much observations of that, I plot the flares Z7 equivalent width functions with respect to some of the observations that are available to us. So here also we have some of these high luminous objects having a higher equivalent width than we have predicted. So it is worth looking into the effect of AGN on these galaxies. So with that, I stop, and here are some of the future work that we plan on doing with these galaxies. So some of the bias, looking at the bias and cosmic variance, the sizes of galaxies, the morphology, and passive galaxies, as mentioned before. And we also plan on looking into the far infrared regime of these galaxies. So looking at some the potential impact for ALMA observations. And we do plan on making a higher resolution simulation to probe the faint, and any ideas and collaborations are welcome. Thank you.
Thank you, Aswin. So we have some questions for you. We'll start with one from Casey Papovich, who asks, at the bright end of the UV luminosity function, do you have a sense of what in the models is driving the exponential cutoff? Why does it look more like a Schechter function than a power law? What physical effects are happening?
So it could be an impact of what is happening with the effect of the star formation rate in these galaxies as a function of the feedback that is happening at these ends. So we haven't actually looked into what effects these have, but yeah, this is something that we need to probe.
Okay, and then another question about dust from Maxine Trivich, who asks, do you have any sense of how the assumptions you make on the dust distribution affect the photometric properties of your galaxies?
Oh, yeah, that is quite a great question. So, so the dust would definitely affect any property that we measure from here, obviously. But so the grain size distribution and the attenuation curve that we actually choose to observe these galaxies would affect what outputs we see. So we did try some other extinction curves from literature, and what we saw was to get back some of these observational results, we do need something like an SMC curve to get back these properties, like the UV continuum slope. And an evolving dust to metal ratio would also make sense, since this is something that has been seen in observations as well as some modeling results. So yeah, these are all something that we definitely need to try and would love to do.
Oh, sorry, I was muted while I was asking you. One last question from Nathan Adams, who asked, do the simulations give any constraints on the AGN UV luminosity function in your lower redshift bin?
So we haven't actually looked at modeling the AGN luminosity function. So it's a work in progress, and we might be able to tell you soon about it.
One more question from Tom Thunes, who asked, what is the faint end slope of the UV luminosity function, and how faint below HST limits do you simulate?
Sorry, could you repeat that again?
They're curious about what the faint end slope is of the UV luminosity function.
Okay, so I do have some of the faint end slope that we tried to look at, and it is quite similar to some of the observational results. So here's a plot that I made of the UV luminosity function. It's the darker points would be the Schechter, and the light gray would be the double power law. So does that answer the question?
Yes, I think so. All right, so I think we should move on, but thank you, Aswin.
Oh, thank you.
And let's move on now to Victoria Strait, whose talk title is Stellar Populations of Galaxies in the Cosmic Dawn with HST and Spitzer. So Victoria, go ahead and share your slides, and you can unmute yourself when you're ready.
Hi, can you all see that and hear me?
Yes, we can.
Thank you, Chris and Aswin, for those nice talks. I'm Victoria, and I'm going to be talking about observations of galaxies at redshift 6 and above using Hubble and Spitzer, to try to see what we can learn before JWST. So the question I'm trying to answer that informs a lot of other questions in astronomy is, what do the galaxies in the Epoch of Reionization look like? And pardon this really basic mini lit review, but locally we can see lots of details in galaxies like disks and outflows of gas and spirals. If we take a step back to redshift 0.1 and even farther back to redshift 2, the picture gets quite a bit fuzzier. We lose sort of this nice picture of structure that we had. And then when we get to redshift 6 and 7, where I start to be able to look at galaxies, we mostly see point sources, or in some cases just red fuzzy blobs. So this gets a lot harder to glean information from these galaxies. And then at redshift 8 to 10, the picture is sort of the same, but the red fuzzy blobs are fewer because these things are fainter and the intergalactic medium is absorbing a lot of the light. So the way that one goes about characterizing a population of galaxies that we can't see very well is with surveys. So there are several examples of lensing and flat field surveys that take different techniques. The one that I'm working with is called the Reionization Cluster Lensing Survey, or RELIX. Unlike the Hubble Frontier Fields, which has taken really deep Hubble data of just a few fields, RELIX has taken a different approach. We've surveyed 41 massive galaxy clusters in order to try to find sort of the brighter high redshift candidates that might be more rare, that might not need as much Hubble data. So we have a 188 HST orbit program PI'd by Dan Koh, along with over 1,000 hours of Spitzer data PI'd by my advisor, Marusha Brodach. And here you can see the clusters we targeted in their Planck mass. They're all sort of the most high mass ones. The science that we're doing in RELIX is mostly high redshift galaxies, but there are also people working on lensing, doing supernova searches, and working on galaxy cluster scaling relations. So of course, I'm focusing on the high redshift sample in RELIX. There are over 300, I think 321 HST selected high redshift candidates. This is a figure from Brett Salmon from a few years ago that shows the apparent magnitude and redshift and then absolute magnitude over here. These are photometrically selected with Hubble, so they don't have spectroscopic redshifts. They're just selected with the Lyman break technique. And you can see that they span from redshift 5.5 to about 10 and several orders of magnitude in brightness. Before I go on, I just wanted to say that Dan Koh has a student, Brian Welch, who's working on characterizing the properties of 3 really cool objects from the sample that are the brightest redshift 6 candidate, which is an arc, the longest redshift 6 arc, and the most distant arc, which is actually a redshift 10. So there are also a lot of spectroscopic follow-up programs going on for the RELIX sample. In particular, my group in Davis is looking at these things with Keck. And generally, we're looking for one emission line, Lyman alpha, which gives us a redshift and tells us maybe something about the galaxy. But even when we know a redshift, we need something else in order to say anything about the physical properties of the galaxy. We need to constrain the rest frame optical part of the spectrum. And so we can basically only do this with Spitzer right now for high redshift galaxies. So I'm going to show this with an example from the cluster Avel 370. This is observed magnitude and wavelength. The black points are my data, and the blue points, the blue line in the back is a best fit template. So these wavelengths are probed by Hubble, and the rest frame optical wavelengths over here are probed by Spitzer, and you can see the redshift PDF in the corner there. So if I do the same thing, but only with Hubble fluxes, this is a best fit template that fits the data pretty well. Here's another example of that, and another one, and another one. So maybe you can see my point that with HST data alone, we get quite a large distribution when we're using SED-fitting only to get the stellar properties of this. So this is stellar mass, star formation rate, age, specific star formation rate spanning a couple orders of magnitude. However, when we add Spitzer, it's more data points, but it's also the rest frame optical, which holds a lot of information about these things. So the distributions get quite a lot smaller. So with that in mind, my job has been to add Spitzer to the RELIX sample for the 300 galaxies that already have HST data. And I'm just going to highlight a few cool galaxies that we've found. The first one is a spatially resolved redshift 10 candidate, first discovered by Brett Salmon. This is a photo of it. And this is his plot, linear flux and wavelength. You can see the 2 Spitzer fluxes here are straddling the Balmer break. Since then, we've gotten deeper data, and we've been able to push upper limits down from about here to quite a bit deeper. And since then, you can actually see maybe you can see this, the dotted line here is the P of Z before we had Spitzer, and the solid line here is after Spitzer. So really the Spitzer fluxes here are what caused us to do you'll see in a second more follow-up with HST on this object. But we were able to do SED-fitting with a couple of different sets of assumptions and get an idea of its physical properties. Since then, we have gotten more HST data. So this is what it used to look like. And you can see several more clumps now. And I haven't analyzed these data myself, but Dan Coe has. And this, the cool result from this is that the HST data alone prefer Redshift 10 solution strongly, even without Spitzer. So you can see the red line here and the red boxes are the low redshift fit, and the blue one is the high redshift fit, which fits much better. And there's a very peaky P of Z here. The second cool object is this one behind cluster Abel 1763, which shows evidence of an evolved stellar population at redshift 8, or as evolved as it can be at redshift 8. The Spitzer fluxes that I'm highlighting here are also straddling the Balmer break, which is basically just showing light from old stars, and meaning that this galaxy is quite old. You can see this peak in the age distribution around right before redshift, right before 10 to the 9. And this is implying quite an early formation time, less than 100 million years after the Big Bang. And the most recent thing we found is a very strong Lyman alpha emitter that we've named dichromatic primeval galaxy, DP7. This is something Deborah Polici and I are working on. We found that the equivalent width is between 200 and 400 angstroms. And you can see the SED fit over here. It's looking quite old as well. After we got this detection with LRIS, we looked again at the HST data to see sort of what was going on, because it's sort of unexpected that you'd have such a booming Lyman alpha with an old stellar population. And we usually use F160 as the detection image, but we found that in several of the other images, there were actually two components. And so you can see a very red component here in the south and a much bluer component in the north. And we were able to separate these in HST for all the bands and measure the UV spectral slope. And we got a very blue -4 ±2 at the top, and a very red +3 ±2 in the southern component. So this strongly supports there being multiple stellar populations. Our current theory for the galaxy is that it's pretty old, but it's experiencing some sort of rejuvenation process happening in the northern component. So yeah, for this galaxy, one stellar population fit is not necessarily the best. The way that we do SED fitting is maybe not the most appropriate here, because it has two different stellar populations. Unfortunately, we couldn't separate out the Spitzer fluxes for this object. But those three galaxies are some examples of 3 objects that we paid special attention to in the sample of 300 galaxies. But just to give you some diagnostic plots of the entire sample, that will be coming out with a full catalog of Spitzer fluxes and stellar properties on for people to play with. I'm sure there are lots of other cool galaxies for you all to find in there. I was able to recover Spitzer fluxes for 208 of these, and 23 were likely demoted to low redshift. And this paper should be done and out pretty soon. So I will wrap up there.
All right, thank you very much, Victoria. So we have some questions. Question from Rebecca Bowler, who asks, how do you know that the red component in DP7 is at the same redshift?
Yeah, that's a good question. We are kind of making the assumption that the components are so close together. It's I don't remember off the top of my head, 0.2 arc seconds or so. So we're kind of thinking that it would be kind of crazy for galaxies to be overlapping in space like that. But the SEDs of each individual component both look like they're redshift 7.
Okay, and then a follow-up on that object from Asami Uchi. He's curious about the Lyman alpha emission line. He says it looks broad. What is the line width? Is there any possibility that this is an AGN?
I don't know that off the top of my head. Deborah's the one that did this emission line analysis, but I think that's a nice idea to look into. I'm not sure.
Okay, and let's see. So a question from Tom Thunes, who asks, how sensitive are your SED fits to getting the nebular emission lines right in the modeling?
Yeah, that's especially a problem for this one because O3 lands right in the middle of channel 2 for this object. We include strong emission lines in our SED fitting up to 2000 and some odd angstroms for rest frame O3. And still, we're getting an old solution here. Of course, if we didn't include emission lines, this would be even more strongly preferred. So the answer is that it is sensitive, and you can see that there are some young solutions that my SED fitting is finding here, but we believe that we're pretty agnostic.
Okay, I'm going to use chair's prerogative and ask a follow-up. How, I mean, the results must be sensitive to how well you're deblending the IRAC photometry. Do you have any sense of the systematic uncertainty there, especially for objects like the one you're showing, which are right on the wings of a nearby bright source?
Yeah, so I don't know a number for systematic uncertainty, but yeah, definitely the way that we're doing Spitzer photometry is very sensitive to the bright sources nearby, but we do a lot of testing on these Spitzer fluxes to make sure that we believe them. And for this one in particular, the fact that it's showing up in channel 2 and not in channel 1 with the same bright source there is why I believe this. Yes, but certainly bright objects can get in the way.
All right, one final question from Rohan Naidu, who asks, what's your interpretation of the positive beta slope? What kind of ages or dust do you need?
Yeah, I don't know the actual numbers for how much dust we would need for that. We're currently working on this project. But I think that that's pretty reminiscent of something like this SED fit here, which looks fairly dusty. And I think that the reddening was around 1, like the EB minus V was around 1, if I remember correctly.
Right. Okay, well, thank you very much, Victoria. We'll move on to the 4th of 6 talks of this session from Lukas Furtak, the very low mass end of the redshift 6 to 7 galaxy stellar mass function challenges and SED fitting. So Lukas, feel free to unmute yourself and go ahead and start when you're ready.
Okay, hi everyone. Thanks, Steve. So yes, I'll be talking about how we constrain the very low mass end of the stellar mass function at redshift 6 to 7. So my name is Lukas. I'm a PhD student at the Institute for Astrophysics in Paris, and I've done this work with my advisors Kim Tech and Matt Leonard. So yeah, let me give you a quick rundown of stellar mass function at redshift 6 to 7. So mass functions at these redshifts have been measured up to now down to 10 to the 7.5 solar masses in blank fields, and down to 10 to the 6 solar masses using strong lensing clusters. So the general trend observed is the steepening, is a notable steepening of the low mass end slope with increasing redshift. However, measuring stellar mass functions and stellar masses is model dependent, unlike terrestrial UV stellar mass functions, because the stellar mass that we get from photometry will depend on other physical parameters such as stellar age and dust attenuation, etc. So this work is an attempt to test how these other parameters and assumptions we make on these other parameters are going to impact the shape of the low mass end of the stellar mass function. So for that, we look at the 6 Hubble-Fonte fields clusters, which are very well studied strong lensing fields with very deep HST photometry. And when I say I look at very faint, very low mass objects, I mean beyond 26 magnitudes. So we really need the strong lensing effect to even detect these objects. And lensing enables us to detect objects down to -12 absolute UV magnitudes, However, that being said, the systematic uncertainties that come from strong lensing modeling actually induce very large error bars in these objects, meaning that let's say we can robustly constrain the faint end of the luminosity function down to -15 UV magnitudes. So I worked with a sample of 300 redshift 6 to 7 galaxies detected in the Hubble frontier fields. And as Victoria has already said in the talk before, what really is crucial to constrain physical parameters at these redshifts is the rest frame optical photometry, meaning Spitzer photometry. So luckily, the Hubble frontier fields have been observed to very deep depths in the Spitzer with the Spitzer telescope. So we have this rest frame optical photometry to constrain stellar masses. So how do we measure stellar masses? Well, that's done through SED-fitting with a code called the Beagle tool. And so in order to test these how these different physical parameters are going to impact the stellar mass function, we first construct a kind of a minimum parameter and assumption model. So SED-fitting configuration where we fix as many parameters as possible and make the simplest assumptions possible. So in this case, we fix the metallicity at 0.1 solar metallicities, assume a constant star formation history, and limit dust attenuation to very low levels. Because since most of these objects have very blue UV slopes, we expect them to have extremely low dust attenuations. And then departing from that model, we're going to just change single parameters and run more SED fits in order to test how these are going to impact the mass. So when computing, so we then use the whole bunch of SED fits that we've done on these galaxies to derive empirical mass to light ratios and convert the faint and UV luminosity functions to stellar mass functions. So since our sample mostly probes galaxies below 10 to the 8.5 solar masses, we combine these stellar mass functions with some high mass end points observed in blank fields in order to constrain the whole shape, the total shape of the stellar mass function, and then fit this with fit these stellar mass functions with first with the classical Schächter function, which you can see on the left-hand side plot. However, as you can see, the mass function departs from the classical Schächter form at masses lower than 10 to the 7 solar masses. So we also fit them with another modified Schächter function that is going to allow for a downward or for a turnover below 10 to the 7 solar masses. However, if you have a close look at the error bars at the very, very low mass end, they become quite large, if not to say very large. Which in this case is mostly due to strong lensing systematics. So at this point, the error bars will also be consistent with the mass function not turning over or even steepening at the very low mass end. So this turnover is not very well constrained. So how do these SED-fitting assumptions now impact the stellar mass function? So for reasons of time, I'll just talk here about the most extreme cases I find. So in this plot up here on the left side, you can see the solid blue line. That's the minimum assumption model that I've shown earlier. And then the most shallow case of stellar mass function that I find is the dashed line, which we get for assuming exponentially rising star formation histories. And the Nash dotted line is the steepest star formation, the steepest stellar mass function I find, which we get for allowing large ranges of dust attenuation within the observed galaxies. So in total, all these SED-fitting models we apply span low mass end slopes from -2.2 to -1.7. So quite a large gap that we get just from changing single prescriptions in the SED-fitting procedure. So why this is important, you can see why this is important on the plot on the right side down here, especially in this panel, where you can see that the low mass end slope and the high mass end cutoff are strongly correlated in stellar mass functions. So that it means we need to constrain both the low and the high mass end of the stellar mass function in order to constrain the whole shape of the stellar mass function. So in explaining where these differences come from, So I've tracked down what happens when we apply exponentially rising star formation histories, and what happens when we apply higher dust attenuation levels. And basically, both can be tracked down to a lack of either a lack of rostrum optical photometry, Spitzer photometry, or simply that the optical nebula emission lines, such as O3 lines and H beta, are redshifted into the Spitzer IRAC bands at these redshifts. So let me first talk about Spitzer photometry. So since Spitzer has a much lower resolution and much worse point spread function than the Hubble Space Telescope, since we're looking at galaxy clusters, which are naturally crowded fields, there are a lot of galaxies, foreground galaxies in it, we get a lot of contamination by either intercluster light or from the cluster galaxies themselves in the photometry of these very faint high redshift objects, especially if there's a bright galaxy nearby. So in the lower frame, you can see a typical redshift 7 galaxy in a Hubble Space Telescope frame versus what the same galaxy looks like in Spitzer. So it becomes very hard to get accurate photometry in these Spitzer frames. So after selecting sources that are that have really absolutely clean and trusted IRAC photometry, this is actually a pretty small sample of our galaxies, and these are mostly bright galaxies. So on the high mass end, so the very faint, very low mass end galaxies, most of them don't have any IRAC photometry in our sample, which means that these very faint and low mass galaxies are going to be mostly constrained by rostrum UV photometry only, which is not really suited to measure stellar masses, right? And these very low mass galaxies are therefore most heavily affected by allowing a wider range of dust attenuation, since dust attenuation is going to affect the UV wavelengths much more than it does the rostrum optical wavelengths, which leads to a slight shallowing in the mass to light ratios for these galaxies when we allow for larger dust attenuation, which then, with a shallower mass to light ratio, we get the steeper stellar mass function in the end. So this is why this explains the steepest stellar mass function that we find. So something like this will typically be somewhat alleviated when we observe descent galaxies with JWST, because the near cam imager is going to be able to get this rostrum optical photometry at the same resolution and depth as the Hubble Space Telescope photometry. So we can there we will be able to constrain the photometry of these very faint galaxies. And there's also been a couple of papers out recently that simulate how some MIRI photometry is going to alleviate this dust attenuation degeneracy. So the second problem, which results in the most shallow stellar mass functions, are these nebular emission lines, which contaminate the rostrum optical photometry. So when applying when assuming an exponentially rising star formation history, we get lower stellar masses by 0.4 dex, so quite a lot lower, which is basically down to a rising star formation history means larger star formation rates, which mean the emission line equivalent widths in the Spitzer IRAC bands are going to be much larger and account for a much larger fraction in the flux, meaning that the same galaxy is going to be fitted with much lower mass. So the overall lower stellar mass distribution is going to result in a shallower stellar mass function. So for this, we're going to eventually require a near-spec spectroscopy of these rostrum optical emission lines to disentangle the emission lines from the stellar continuum in order to constrain stellar mass. Another parameter that is heavily affected by this is the stellar age. So usually when SED-fitting high redshift galaxies, one just leaves the stellar age and the stellar mass as free parameters. However, we find that by doing this, we basically allow for a too large a range of equivalent widths. So when just changing the lower boundary of stellar age in this kind of fit from 10 million years to 20 million years, or the other way around, from 20 million years to 10 million years, we get a difference in resulting stellar mass distribution of 0.5 dex when just changing the lower boundary of age. As you can see in this plot over here, you see the best fitting SED for a galaxy, and in red you see the best fit with lower boundary of 10 million years, and in green lower boundary of 20 million years. So you need to be, while nebular emission is very important to correctly model these as the SEDs of these sources, so nebular emission needs to be included. However, need also to be careful what then happens, because including nebular emission means that we cannot, at least at redshift 6 and 7, where most of the optical emission lines are redshifted into both the IRAC frames, we cannot really disentangle the nebular emission from the stellar continuum. So as I said, this will mostly, new constraints on this will come with the JWST near-spec spectrograph, which will be able to measure these equivalent widths at these redshifts. However, this will mostly be able to measure them for the bright, so the high mass end galaxies, meaning that on the very low mass and very faint, very low mass end, we will still be dealing with some of these issues, even in the JWST era. So let me leave you here with my summary slide. So while we do observe stellar mass functions down 10⁶ solar masses, we do also find them to be heavily affected by SED-fitting assumptions and prescriptions on the parameters. So they span a range from -2.2 to -1.7 on the low mass end slope, mostly due to either the lack of accurate rest-time optical photometry or due to contamination by the nebular emission lines. A third point I've not been speaking about here because of time is that we also get very large strong lensing systematics, which induce very large uncertainties on high magnification factors, i.e. on the very low mass, faint low mass and galaxies. Right, that's be from me, and thank you for listening.
All right, thank you, Lukas. So I think we have time just for one question. And so, well, with the most votes, where did it go? From Nathan Adams, who asks, how have you handled sample completeness in the low mass regime?
Sample completeness in this case was computed for the UV luminosity functions. It was computed by modeling, basically by injecting sources in the source plane and then running them all the way through the lensing model to see how they arrive in the image plane.
All right, well, thank you very much, Lukas. We'll move on to our next talk, which is from Rebecca Larson. And the talk title is Islands of Reionization. So Rebecca, when you're ready, go ahead and share your screen and you can unmute yourself and get going.
Thank you, Steve, and thank you, Steve, and the rest of the SOC for putting on this conference. I really appreciate the opportunity to give this talk, and I wanted to give another special shout out to all of my collaborators I've listed here, many of whom are at this conference, so a virtual hello to you. Can't wait till we can be at the next conference in person together. So today I'm going to talk about a program called the Islands of Reionization, which is a Keck program that I've been working on for the past couple of years now. And it's looking for high redshift galaxies. And so I'm just going to talk about the most recent results that I have and update everyone on where I'm at. So this program is looking for redshift 9 Lyman alpha emission. And that sounds like a very daring thing to try to do with ground-based telescopes, especially given the fact that this redshifts is where Lyman alpha ends up in the infrared. And so why are we trying to do this, and why do we think that we can do this? Well, there's a couple different reasons, and I'm glad I don't have to do a whole intro about reionization to this particular crowd. And so there's a lot we don't know about the reionization era. We don't know what the source of the reionization photons were, and we don't know exactly when it started or how quickly the process went forward. So here I'm showing a plot that has the ionized volume fraction, so how much of the universe is ionized on the y-axis, and then redshift on the x-axis. And so here we're showing two different theories and models of how reionization could have happened. And so this first one I'm going to show you is this gray line right here. And so this assumes a uniform escape fraction of ionizing radiation from every galaxy. And so what you end up having is you have high mass galaxies producing most of your ionizing photons, but it does take time to build up high mass galaxies. So this reionization process starts a little bit slowly, but then once you get big galaxies, you actually can ramp up and ionize a greater portion of the universe much faster. But if you assume that the ionizing escape fraction is actually halo mass based, then you actually have ionized photons escaping from low mass galaxies early on. And since there are more low mass galaxies, and because they are formed sooner, we are able to start this reionization process earlier, and it doesn't have to be such a drastic ramp up. And so the time in history in which these two different models are the most discrepant is redshift 9. And at redshift 9, one theory will predict that only 10 to 20% of the universe will be ionized, and then the other one would predict that 60 to 70% of the universe will be ionized. So if we assume that about 60% of the universe is ionized, we should be able to see Lyman alpha. And that is because Lyman alpha will resonantly scatter out of phase if the ionized bubble is large enough. And so if you have an ionized bubble that's about a megaparsec across, you would be able to see Lyman alpha along that line of sight. And so what we wanted to do was to target galaxies that we thought would be some of the ones that are in those ionized bubbles early on. And so we looked for high redshift galaxy candidates in the cosmos field. And this is a paper by Steve Finkelstein in prep for this year. And we looked for galaxies that have neighbor subtracted IRAC photometry. They were visually inspected. We checked for persistence and were very careful in all of the things that we were looking for. And so our final sample of galaxies is around 11 redshift 9 to 11 galaxies across all 5 candles fields. And we also looked for the ones that had high ionizing photon fractions because we looked for the Spitzer IRAC colors where the O3 would have been bright. And so we had red IRAC colors indicative of high ionizing radiation. These would be the galaxies that would be most likely to be in an ionized bubble because they are emitting enough of that high energy radiation. And so what we did is we targeted these galaxies. We got time on the telescope for 4 semesters, 2 nights each in 2018 and 2019. And then we also had 2 nights in 2020 through another program PI'd by Taylor Hutchinson. And so she will actually be talking about her portion of this, this science in our next session. So we used the Keck Mossfire spectrograph, which is a multi-object spectrograph. We looked in the J band, which is 1.15 to 1.35 microns, which corresponds to a Lyman alpha emission around 8.5 to 10.1. And so we can actually observe about 30 objects per mask, but we only have about 2 to 3 at maybe 5, if we're lucky, of our redshift 9 to 10 objects that fit in one individual pointing. And so we actually filled the slits with some lower redshift 5 to 7 galaxies looking for UV nebular emission lines like carbon-3 and carbon-4. And again, I will encourage you to watch Taylor's talk later today about that science. And so we also placed 2 stars in our slits so that we had a good understanding of where everything was lined up, and because we needed to be able to see something with continuum to make sure that we were having good observations and nothing was going wrong. So I have a list here of just all of the different observations that we took. So there's a known problem with Mossfire, and that is that over the course of a night, if you observe for long exposure times, you actually find that your objects drift in the slit. So from where they're expected to be in your detector, and if you expose for a long amount of time, they actually start to drift. So this plot that I'm showing here is over time. Some of our observations were over 6 hours. We are watching the drift of the object every 5 minutes. And so here we're looking at those stars that we put in slits so that we can measure this effect. And this is something that we had to incorporate into our data reduction on top of running it through the pipeline and making sure that we were lining everything up and accounting for this drift, because we need every photon possible if we're trying to do Lyman alpha at redshift 9. And so we are using an offset relative to the first frame. And the reason I say relative to the first frame is because we also found that some of our objects were offset from where they were expected to be in the slit. From the position the pipeline says that this object should lie in your detector, it was actually off. And so in order to account for this, we came up with a different kind of extraction method. So here we use that slit star where you are getting a positive trace and 2 negative traces due to our dither pattern in Mossfire. And a continuum source would look like this model right here. And so what we wanted to do was boost the signal of real lines by using the profile of an actual line, including the 2 negatives as our extraction profile into a 1D spectrum. But the problem we found was that some of our objects were offset. And so what we needed to do, especially for those objects like redshift 9 Lyman alpha galaxies, where you do not detect continua, and you have to look for very faint emission lines, we wanted to make sure that we were looking at every possible position that our galaxy could be at. And so we took a look at all of the galaxies that we had as filler targets and our stars and brighter sources that we were able to detect continuum, and found that they were offset between -3 and 3 pixels from where the pipeline expected it to be. So here at the bottom left, I'm showing that same emission line at the top, but showing you exactly where the center is supposed to be in the pipeline, but also showing you that this bright blue line is actually where the center of the object is. And so it is offset from where the pipeline expects it to be. In order to account for this and to correct for this, we extracted with this weighted extraction profile at all 7 of these offsets for every single one of our galaxies for every night. You can see on the right here that when we actually line up our extraction profile, we get the full flux from our emission line. For this particular bright low redshift line, we would detect it no matter which offset we use. But when we line up the model with the correct center of our emission line and our galaxy, we get the full flux. And so this is exactly what we want to do for faint lines, is get the most amount of flux possible and be as accurate as we can. But like I said before, we don't exactly know where our object is in the slit if we can't see the continuum. So we did a rolling extraction and had 7 different centers for every time we observed a galaxy. And so sometimes we observed a galaxy 3 different times in order to get the total amount of exposure time we needed to potentially detect these lines. That means that for every night we had 7 possible spectra, and we had 3 nights, which is 343 different combinations for just one galaxy to try to find the line by matching them up. Thankfully, in 2018, I worked on an automated line finding code that I used to look for Lyman alpha at redshift 7 in the Hubble GRISM data. And I used that same code to automate a search for emission lines in every single one of these 343 spectra. And so what I looked for was emission lines that were greater than 2 sigma in any of the combinations. And then I looked for the combination where we found it with the highest signal to noise. So when we matched all of the offsets correctly, we get the total flux of the line that we detected. And so we also had to do away with the skylines. And so all of this process is quite detailed, but I'm going to skip over it for this short talk and just show you some of our preliminary results. So this result right here is a Lyman alpha emission line that would be at redshift 8.7. And so here on the left, I am showing just a Hubble image stamp showing the 2 slits that we had with different orientations for this object. A total exposure time of 9.5 hours for this over 3 different nights with an average seeing of 0.7 arc seconds. In fact, this is probably our best data that we got. And so I'm very happy that in our best data, we actually have a detection. I'm showing the IRAC postage stamps at the top where we do have that red IRAC color indicative of potentially strong O3 emission. And so our photo Z is around 8.9, meaning that we're doing a pretty good job of getting all of our photo Zs for our target galaxies. Here I am showing in the 2D the counts per second. So this is our data. And then here is a signal to noise of this same emission line. Like before in that example of the low redshift object, you would expect to see a very bright emission line in those pink circles, and then 2 negative traces in the teal circles. And to the right, I'm showing the extracted 1D spectra, where we find the line in both nights individually with our line finding code, but we also find the line at the same position in the stack of those 2 nights together. So I said I observed this night 3 times, but the night that we observed it with 1.3 hours was very bad seeing and was very noisy data. And so we decided overall, we're going to remove any one of our nights that have less than 2 hours of exposure time because they do not add to our science. So this is exciting in and of itself, but the more exciting part about this is that this particular object is physically very close to another redshift 8.7 galaxy that we already knew about. Adi Zitrin in 2015 found this Lyman alpha emitting galaxy, and I've drawn this circle right here. Behind us is a stamp of the candle's EGS field. And so you can see that a lot of our targets here are in the EGS field, and the green squares are where we put our Mossfire pointings. We didn't look at Adi Zitrin's object because we already have a redshift from it. And so we focused on getting data from some of our other candidate galaxies. What's interesting is our redshift 8.7 galaxy is over here. And if you do some cosmology calculations, you find that these 2 galaxies, given that they're at the same redshift, are only 3.5 megaparsecs away from each other in proper coordinates. What is also interesting is this object that we found Lyman alpha in 2015 was also found to have a nitrogen 5 emission line in 2018. And that means that there's probably an AGN, which would also increase the amount of ionizing photons that are escaping from this galaxy, potentially making the bubble around it much bigger. And so what are the implications for reionization from this detection and from our whole survey? Well, 2 of our 9 targets have tentative Lyman alpha detections, including this one from Zitron in 2015. And since they're physically close to each other, there's potentially an overdensity in EGS. In fact, 5 of our 9 total candidate galaxies are in EGS, which is already indicative of a potential overdensity at this high redshift. And so overdensities would actually be the things that reionize first, which would make it much more likely for us to detect Lyman alpha. And so it's already a serendipitous detection of nitrogen-5 that includes even more ionizing photons, meaning this is even more likely to be an ionized bubble. We still have a lot of work to do. I'm not done finishing all of our data analysis, but I'm happy to announce that I am finally done with the data reduction. And so if we confirm this line, this could indicate large ionized bubbles as early as about redshift 9. So I'm going to leave that there and go ahead and take questions. Thank you.
All right, thank you, Rebecca. So the first question is from Sarah Bosman, who asks, are the Mossfire offsets between exposures you find consistent with the positions of other bright objects in the same slit as this galaxy?
Yes, so all of the offsets, when we did, we decided to do -3 to 3 pixels as our range of extraction centers because we looked at the objects that we were able to see in continuum in that same mask and found that they ranged from that range of offsets. And that's why we decided to use those as our extraction centers. Now, it's also a problem when we have contaminating sources and things like that. And so there's a lot of other things that I didn't include, but that was why we use those extraction centers.
Okay, and one last question from Ryan Ensley, who asks if you're willing to share the UV magnitude of the source.
The UV magnitude of this source, I believe, is 27-ish, but I will have to look up the exact number. I don't have that written down right now.
All right, that was a quick answer. So I'll give you one more from Dan Coe, who asked if your results help constrain the reionization histories that you showed back in your introductory slide.
So I am hesitant to kind of make that that broad thing without having looked at all of my data so far. I was still trying to go through all of that late last night. So with this one detection, I think it's interesting that we're seeing potentially this overdensity, and maybe that's just a serendipitous line of sight or a situation that worked out in our favor. But if we are able to constrain the likelihood of seeing something like this overdensity with some of the theoretical models, then we would be able to say how likely we were to have found this, and then maybe use that information to make an estimate of how much of the universe was reionized at this point.
All right, thank you very much, Rebecca.
Thank you.
Let's move on to our last talk of this first session by Aaron Young, whose talk title is Semi-analytic Forecast, Uncovering Galaxy Formation with JWST and Beyond. So Aaron, when you're ready, go ahead and share your screen and you can unmute yourself.
Thank you, Steve. Sorry. Hi, everyone. My name is Aaron Young. I'm a graduate student. Oh, no. I have recently graduated from Rutgers, and I will remain in the Flatiron Institute until the end of the summer. Then I'll move to NASA Goddard as an MPP fellow this fall. So I would like to thank the organizers, especially the Steves, for making this fun escape from quarantine possible, as I'm still currently based in New York and have been locked up for many months now. In the next 10 minutes, I will give you an overview for the semi-analytic forecast for JWST work series. And at the end, I'll give you a brief forecast for the future of the forecast project. Great. So I don't think I need to convince this audience why we want to explore the very high redshift universe. There are just so many things that we don't know yet, and we are about to find out more with our shiny new tools. And JWST is one of them. So before I get to the forecast for JWST, let me first briefly walk you through the model that we use to make the forecast. In this project, we use the Santa Cruz Semi-analytic model, or SAM, to model galaxy formation at high redshift. The physical processes that are involved in galaxy formation are tracked with a collection of physical or empirical recipes. And this includes the very standard things like the cooling of gas, star formation, supernova feedback, and many other things. And of course, we also have a new gas partitioning recipe that partitions cold gas into different phases, for example, the ionized, neutral, and molecular phase. And we also get, and we also use the molecular hydrogen as a tracer for star formation. And because the SAM is very efficient, and we also get a predictions for a wide variety of physical properties out. For example, the star formation rate, stellar mass, size, metallicity, and UV luminosity. And the list goes on and on. And since galaxy properties are being tracked in bulk, we don't keep tabs on hundreds or thousands of mass particles or grid cells. And our model is much more efficient than conventional numerical methods. And because of that, we can easily simulate millions of galaxies across an extremely wide mass range and also a wide range of redshift, and only requires a rather scalable amount of time and computational resources. So all sounds great, right? Except this is, well, this is great, but at some cost. So this modeling approach, we are not able to spatially resolve our galaxy. So we can't see the internal structure. We can tell how stars and gas are distributed within the galaxy. And SAM is not great at accounting for effects from the environment. So for now, the current SAM doesn't know about a galaxy nearby if there is one. It just tracks whatever physics happens within a halo or within its own merger history of the halo. Great. So we have heard a few talks about galaxies, but let me also try to take this opportunity to make a little connection to cosmic reionization. So we take the predicted galaxy population and specifically the stellar mass, star formation rate, stellar age, and metallicity. And then we use a synthetic stellar population model of our choice. In this case, our traditional model is BPAS. And then we calculate or predict the production rates of Lyman continuum photons. So this gives us the cosmic ionizing photon budget, or we can call it the source term, and in the following differential equation. And of course, there is also a sink term that represents the recombination of ionizing hydrogen, ionized hydrogen. And solving this equation gives us the bulk estimate of the cosmic reionization history as a function of time. Great. So this model is certainly not new. It's been developed quite a while ago, but here there are a few things that we did slightly differently in attempt to make this model a little more physical. So first, our galaxies are sourced from a physically motivated SAM. So we sampled objects across a very wide mass range, and this means we're doing fewer extrapolations, but rather to make sure our galaxies are physically backed. And secondly, the production of ionizing photons is calculated based off the star formation history of individual galaxies. So we can capture more of the correlation and scatter of Lyman continuum production rate and other galaxy properties. And overall, there are fewer smoothings and fittings. So we simply sum the contribution of all our predicted galaxies instead of having to integrate over the fitted UV luminosity functions. So that all helps a little bit. All right, so here comes the result. First, let me show you our predicted UV luminosity function at redshift 4 to 10. The blue solid lines are the predictions from our traditional model. The dashed lines show what happens without dust. And of course, the data points are from observations. We see that 3 parameters in our model are only calibrated to redshift 0, but these predictions are doing, I would say reasonably well, but it's actually exceptionally well matching observational constraints, and this is non-trivial. And these predictions extend to very faint magnitudes that we hope in the future JWST will be able to finally reveal. All right. And because the SAM is super efficient, we can also explore how results are impacted by different model assumptions and by doing some controlled experiments. So we know that stellar feedback is a main mechanism that can suppress or boost the number of faint galaxies. And the equation in the box here is what we use to track mass outflow due to supernova feedback. And in our experiment, we changed this one particular parameter, alpha reheat, to explore alternative scenarios where the strength of the supernova feedback is stronger or weaker. And we then provide a range of predictions that are still permitted by the current sets of observations. And hopefully in the future, JWST will be able to narrow that down by a lot. Great. And last for this part, I just want to quickly flash a collection of cross correlations that we predicted for the many physical properties we get out of the SAM. The cyan and purple lines mark where we expect a JWST wide of view deep survey will show us. And if you're an observer, you might find the bottom row handy, as it shows a range of some key corresponding physical properties for galaxies at a given observed magnitude. Okay, so those were the galaxies, and let's switch gear a little bit to talk about reionization. So the theme here is to try to understand and perhaps to disentangle the three moving parts that have significant impacts on the overall cosmic reionization ionizing photon budget a little bit. Let's start with the figure on the left. There's one figure right now. The first moving part is the production rate of ionizing photons, which has to do with the physical properties of the stellar populations and how it's translated to the number of ionizing photons being produced, and which depends largely on the assumptions that went into the synthetic stellar population models. So here I show you two examples. The blue line is our traditional model with B-pass binary, and which accounts for binary stars, obviously. And in comparison, we also show you an older model that the purple line is the model that only account for res UV magnitude. So it's just taking the magnitude of a galaxy and translate that into the number of ionizing photons being produced. Okay, so we already see that there's a little difference, but we don't stop there. So the second moving part is the number of galaxies that are out there. So from the last slide, we know there are, well, they're quite literally, we're asking how many galaxies are there in the high redshift universe. And we saw that the supernova feedback mechanism can have a huge impact on the fate and slope of the luminosity function. So this is basically the same from what we saw from the last slide. We ask what will the ionizing photon budget be with these different predicted, the range of the ionizing, of the UV luminosity functions. And of course, the last part, we allow the alignment continuum escape fraction to vary from 5% to 80%. So note that for this part, we just let the escape fraction to be a constant over time and for all galaxies. And this already shows us this. For the entire set of this controlled experiment, we only vary one thing at a time, and you can very clearly see how each part, what role do they play in affecting the global ionizing photon budget. All right, so on the right, we then jam this whole thing into an MC hammer, trying to figure out the optimal configurations that are needed to reproduce the set of current observations. And the top panel on the right shows you that all we need is a redshift dependent escape fraction that evolves from a few percent to a 25% at high redshift. And of course, what is nice is the predicted alpha reheat is quite similar or very close to our traditional value. And this is what it all takes to reproduce the current set of observations for observed constraints on reionization history, which is great. I'm happy. All right, ultimately, we want to answer some of the questions. For example, like, what fraction of ionizing photons are coming from the detected galaxies? So for example, here we can see for a JWST deep survey, we are expecting, well, on the left, we're expecting maybe about 40% with the galaxy that are expected to be picked up by JWST in a deep survey will be accountable for about 40% of the overall ionizing photon budget at redshift 10. And this goes up to about 80% at redshift 6 toward the end of reionization, which is great. So we are looking at galaxies that are doing most of the heavy lifting. So similarly on the right, I break down the predicted galaxy populations to 4 groups and their res UV magnitude and to plot their contribution as a function of redshift. And we can see that galaxies that are contributing the most ionizing photons are not the brightest ones, since there are only very few of them. But it is slightly fainter. It is the slightly fainter ones that are doing the heavy lifting, which are both very prevalent at high redshift, and also they are quite efficient at producing ionizing photons. Great, so there are so many things I want to cover, but I really have to let some of those go. But I do encourage you to check out the work series. They're all been published or accepted. And before I go, I just want to use 2 more slides to show you some exciting future work that we plan to do. So there are 2 parts of the plan. One is to keep working on the forecast project to make SAM a platform for multi-instrument exploration. So I'm happy that the newly renamed Roman Space Telescope will proceed. And we now have these 2 square degree light cones, which is a simulated field with the good south field in comparison on the top. And you're looking at galaxies with positions in the sky and also a redshift gradient. So we can now use these new light currents to explore some large survey exclusive science, such as clustering. But also there's a separate theory project called Samurai, which is what I'm going to do at Goddard, which stands for SAM with ultra high redshift astrophysical interplay. We'll be implementing a few, hopefully more high redshift exclusive or very important physical processes at high redshift. So to make the model more physically representative for the high redshift galaxy population. All right, so I'll leave you with the conclusion and outlook. I know I'm running out of time, but please do reach out to me. I have a new email address, and looking forward to answer any questions.
All right, thank you, Aaron. So a couple questions on the escape fraction. So from Maxime Trebich, have you tried to implement an escape fraction dependent on galaxy properties such as stellar mass, specific star formation rate? And Christian Fenlater says along those lines, is a redshift dependence still required even if a mass dependence is allowed?
Thanks for all those questions. I've gotten those from co-authors, from the referee, from the editor, and also from everyone who have seen this work in the past. Yes, that was the plan, but it turns out to be too messy, and I probably won't be able to finish that when I graduate. But we do have a few plans that goes from very simple things to have the escape fraction scale with individual halo mass, or even with dust. So there are so many venues that there's so many directions that we can take this. And I'm really excited about building a slightly more sophisticated and more physically representative escape fraction model, but we want to do it right. But yes, if you want to talk more offline and give me a little input how to do it, I will be super happy.
Great. All right, well, thank you, Aaron. And that concludes this morning's session. We're a few minutes over because of Steve and my long-winded introductory remarks, but the next session will start in just about 25 minutes at the same webinar and also on the YouTube live stream. In the meantime, take a break, have a coffee or a Sazerac, whatever you like. And if you would like to, we're going to have a discussion on sharing ideas for improving or rather wiping out structural racism at universities. That Zoom link is in the email and also in the general window on Slack. So if you'd like to go there, we'll wait 2 or 3 minutes to get started there. Otherwise, we'll see you back here in about 25 minutes. And thank you to all this morning's speakers.
Can I just ask the next group of speakers to stay online so I can promote you to panelists and we can check your connection and whether you can share your slides. And I'll try and promote you to panelists over the next few minutes. Taylor, would you like to try your audio and try screen sharing?
Steve,
Sure.
do you want to stop the live stream first?
Yeah, I didn't know what the consequences of that would be, but do you reckon I can stop it and then easily restart it?
I think so, but I don't know if it'll be the same video, if that's okay.
No, it'll start as a new live stream, but for each session, that kind of makes sense.
Mm-hmm.
Okay.